All right, like I said, we're going to start chapter 10 today, which is on data-driven analysis of nonlinear resonances. We're really going to pull together pretty much a lot of the concepts that we've been dealing with in this class, going all the way back to maybe chapter 2 and chapter 3 as well. We're going to start by talking about the averaging theorem, and some of you may have seen this if you're doing an independent study with me. Otherwise, you may not have seen it before. We're going to go over what the averaging theorem is, and then use it as a way to study nonlinear resonances. So we're going to first start by considering the dynamical system x dot under bar. So it's a vector is equal to here epsilon, f under bar, x under bar, t, and t comma epsilon, where here epsilon is our small parameter. And x lives in the domain U, which is either equal to the real numbers or a subset of it, of Rn. And here, this epsilon is greater than 0, but less than 1, we'll say. And so here f is a mapping from Rn by R plus to Rn, and it is C in the domain Cp, meaning that we can take up to p derivatives where p is at least equal to 2, and it may be larger. We're also thinking that it's bounded in bounded sets, which just means that so long as we give it bounded initial conditions, non-infinite initial conditions, we get back a non-infinite response. And it has a period of big T, which is greater than 0, and lives in, time is a little t here. And again, we're just going to restrict our analysis to some bounded set in the real numbers, or some subset of the real numbers. And then doing that, what we can do is we can construct an autonomous form of equation 1 by averaging the dynamics over one period. And doing so results in the following autonomous average system, which we'll say is here y dot, which is still a vector, is equal to epsilon divided by big T times the integral from 0 to big T of f acting on y comma t comma 0 dt, and we will define this to be epsilon times f tilde under bar of y. And so that tilde here is used to represent the average version, average autonomous function, instead of the non-autonomous function we started with. And here we've averaged with respect to omega, our frequency omega, which is 2 pi over big T. We're averaging with respect to one cycle, one period, and you often hear people talking about averaging with respect to a particular frequency. In this case, usually a fast frequency, in this case omega. And when we say provided omega is of at least order 1, that means it's again a fast frequency rather than a slow frequency. And we'll see what I mean by slow frequencies and so forth, but you've encountered these ideas previously. Okay, so the averaging theorem states that there is a change of coordinates from x to y such that equation 2 ends up becoming the following: y dot is equal to epsilon tilde of y, so that's our average dynamical system, plus epsilon squared times an f1, which is now a function of y comma t comma epsilon. And where again f1 here is still a period big T. So what we've done is we have effectively extracted out some leading order dynamics in terms of an autonomous system, and then taken all of the non-autonomous stuff and some other weaker effects and placed them into this F1. All right, so I'll also say that you guys won't be expected to apply this in application to any kind of dynamical system. we are going to use the results of the averaging theorem, or specifically the failure of the averaging theorem, to establish when resonances can occur. And then we'll move forward and do that with data. Okay, so often the average theorem is applied to partition the dynamics into fast and slowly varying components, generally by averaging out the fast dynamics and leaving only the slow dynamics. So the fast dynamics evolves with time t, just like what we saw when we dealt with multiple scales. And the slow dynamics will evolve with time epsilon t. So often you can decompose this dynamics into amplitudes and angles, where the angle might be also called a phase, and in which case you are going to perform this averaging over angles. So if you think back to when we dealt with multiple scales, we generally ended up expanding into a polar form where we had some complex amplitude and some complex phase that we were studying. Similar idea here. In this case, we're dealing with multiple degrees of freedom, not just one or two. And in that case, we can end up expressing this average dynamical system as the following. We're going to have a vector of r dot and theta dot. So the r's here are our amplitudes, and the thetas are the angles or the phases. And then this is equal to, for r dot we'll have 0, for the thetas we'll have some omega 0, which is a function, in this case, only of the amplitude. Plus epsilon times the quantity F1 of R, comma theta, comma epsilon, and then below that we'll have some capital omega 1, which is a function here of R, theta, and epsilon. With some kinds of initial conditions, r of 0 equal to r0 and theta of 0 equal to theta 0. Here r is in the domain Rn and theta is in the domain Tm, where this T represents a nth dimensional torus, and epsilon is a small parameter. Yep, and like I said, Tm is the M torus such that theta lives in the domain Rm, and these functions, f1 and omega 1, are 2 pi periodic and in each of the components of theta. All right, so in many applications, the angles in theta will tend to represent a difference between two phase variables, two phases. For example, the difference between the phases of two particular n and m's. We're going to use that to our advantage when we start looking at what resonance is and establishing resonance between different modes or different degrees of freedom and so forth. And we're going to follow the discussion or base our discussion on section 5 of Sanders. And if you look at the bottom of the page, you'll see that's where that reference is. If you're interested, I will be happy to share the PDF for this. But moving on, we are going to just simplify our discussion by setting that omega 1 function to 0, such that we will get our dynamical system reduced down to r dot theta dot is equal to 0, omega 0, only a function of r here, plus the quantity epsilon times that quantity of f1 of r, theta, and epsilon, and then just 0 down here. So resonances are going to occur whenever this omega 0 term, whenever that is 0, or approximately equal to 0, which means that the frequencies of two of the particular phases are about equal. So we're again thinking about a phase difference, or the difference between two phases, and if this omega term goes to 0, then it implies that they have frequencies that are about equal. All right. So in chapters 4 and 5, we studied how internal resonance rose between two modes. That was in chapter 4 when we dealt with multiple scales for two modes. And in chapter 5, we looked at it for two NNMs. And we found that this occurred whenever their frequencies were approximately rationally related by some integer ratio. What else? We saw that the two modes could interact through those rational combinations of their frequencies and so forth. So when m is greater than 1, and if I just scroll back on up here, so m is equivalent to the number of angles that we're considering here. When m is greater than 1, more than one angle, which is true in any multi-degree of freedom vibrating structure, there's really no general theory for resonance that we can establish. So you end up having to study each particular system individually, and all kinds of interesting things can happen. You can have resonance cascades or different types of integer ratios that pop up and sweep through as the response progresses. You can get one-to-one between two different NNMs. You can get or one-to-one between 2 degrees of freedom, like 2-to-1 between 2 degrees of freedom, and we're going to see a bunch of these kinds of things. Point is that it's very complicated, and as a result becomes very interesting to study in general, and makes it difficult for us to give a general theory. So we're just going to focus on the case where m is equal to 2, which is just where we have two phase variables, and this implies that there's just two NNMs participating in the response, and we have n spatial variables. So in this case, we're going to write this as the dynamical system as r dot and theta dot are equal to still the quantity 0, omega 0 of r plus epsilon, and we're going to replace that f1 with a big R1, which is now just a function of r and theta. We'll call that 0. And here r lives in Rn, and theta lives in the 2 torus. And then there is the reference at the bottom.
Sorry, is this one, when you say R1, F1, is it the first derivative?
No, it's just a function.
Okay.
It's not a derivative. Yeah, that's a 1, not a prime or anything. And there, if you're interested in how we would find like R1 or F1, you can read the book. It goes through that. Like I said, we're going through section 8.5, so there's 8 chapters or 7 chapters that we've skipped to this point. All right. What we're going to do now is we're going to expand the right-hand side of the equation for R into a complex Fourier series. And doing so results in the following, that this R dot will be equal to epsilon times the sum from k comma L equals minus infinity to infinity of some coefficient C sub KL. Sorry, this is a function, depends on R here, times E to the J times K theta 1 plus L theta 2. And so based on this, we will find that resonance occurs when K times omega 1, 0 of R plus L omega 2, 0, also function of R, whenever this is equal to 0. Okay, so what this says is that the frequency, these omegas that I've circled, whenever those frequencies for the first phase, that would be this guy, and the second phase, this one, whenever they are related by some ratio k to L, that is when we're going to get resonance, which is again what we saw when we did multiple scales and we looked at the nonlinear normal modes as well. Okay, so outside of resonance, if you do averaging, what you end up with is that y dot is equal to some function c0, 0, 1 of y, meaning that we can average out all of the non-autonomous stuff and get back only an autonomous equation. Like I said, the details of what that really means is in the book, and we're going to skip that. What we're interested in is what happens when resonance does occur. So in the part of Rn where resonance occurs, then what we want to end up doing, or what ends up being natural to do, is to introduce two linearly independent combinations for those angles theta 1 and theta 2. One of those combinations is going to be chosen, or we are going to choose it to be the following. We're going to say that phi sub k to L, we're going to say this is k times theta 1 plus L times theta 2. Then the equation governing this phi here is going to be slowly varying in the neighborhood where equation 8 is satisfied, our resonance condition. And as a result, you will not be able to do averaging over this phase variable. So what that means is that if, well, we'll get to the moment. So because this angle is slow, you cannot do averaging, and our averaging theorem then fails as a result. And so our key idea here is that if we can find some type of slow angle in the dynamics or in your measurement, then you can demonstrate the existence of a nonlinear resonance via the failure of this averaging theorem. And that's what we are going to end up doing. And we're going to come back and stitch a bunch of things together. We're going to start with slow flow dynamics, which we touched on when we did CXA, which I think was in chapter 3, into chapter 3. We're then going to look at empirical slow flow dynamics using empirical mode decomposition and establish a physical correspondence between the two. And then we will then use that to create these phase variables and demonstrate the existence of nonlinear resonance. And then we'll look at 3 examples. Okay.
Could you say that again, why it fails?
So if we go all the way back up to here, so here, equation 2. So we can only perform this averaging provided that omega is of order 1, or is a fast frequency, which means that if you were to compute the equivalent phase for that omega, you would find that it's a fast varying phase. When you have a slow varying phase, you're not allowed to do this. The averaging thing then fails, actually. And the book in chapter 7 goes through some examples where this happens, actually. We won't really go through that here. But we will end up demonstrating like what is a fast phase versus a slow phase in terms of this analysis. We will discuss that. Any other questions? Okay. So like I said, in chapter 3, we dealt with the method of complexification averaging. We looked at just a single degree of freedom. And the key idea there was that we wanted to complexify the dynamics so that we can then do a decomposition and separate the response or the dynamics into fast and slowly varying dynamics. We're going to apply a very similar approach here, except that rather than dealing with just 1 degree of freedom, we're going to deal with multiple degrees of freedom and assume that each degree of freedom is made up of multiple components as well. All right, so we're going to start off just by considering a strongly nonlinear dynamical system. And by the way, we were previously looking at weakly nonlinear dynamical systems, but the results from what we just studied are applicable in cases of strongly nonlinear. All right, so we're going to consider the following dynamical system. We're going to say big X dot is equal to some function f of x, and it could be a function of time as well. And here x is defined to be the vector of x and x dot transposed, and that lives in the domain 2n, r to the 2n, and time here lives in r. So we're now just considering a state space version of some vibrating structure, where x represents the displacement and x dot is the velocities. And here this f, it maps the domain r2n by r into r2n. And again, we're going to assume that it is CP continuous, and I believe this P here should still actually just be a 2, not an N. So small n is, again, the number of degrees of freedom we have, and if it needs to be, P needs to be equal or greater than N, then that's a much stronger constraint than 2. Again, assuming that it's bounded, unbounded sets, and it's periodic in T here. All right, so we're going to start by assuming that the dynamics contains big N distinct components, which is not necessarily equal to the number of degrees of freedom. It could be more, it could be less. And that each of these components occurs at some characteristic frequency ordered from omega 1 to omega big N. And doing so, we can express each degree of freedom as a summation of those components, or that xi of t, which is our ith degree of freedom, is equal to, we'll just say xi1 of t here, plus all the way up to xin of t, where again here I is equal to 1 all the way up to little n being the number of coordinates or degrees of freedom. Big N is the number of components or the number of nonlinear normal modes that are activated or participating in the response. And big N is not necessarily equal to little n, and here x sub im denotes the response of the ith coordinate or degree of freedom associated with that frequency omega m. These characteristic frequencies are going to be called the fast frequencies, and they're ordered just as you would expect, with 0 being less than omega 1 being less than omega 2, and so on until we get to omega n. Okay, so if we're thinking of some type of continuous structure that is vibrating, it's going to have an infinite number of modes due to having being a continuum. However, it's unlikely that an infinite number of modes are actually participating in the response due to damping. Damping would tend to kill out higher frequencies unless you are directly exciting them. So that's where this assumption comes in, that there's some discrete number of components or modes or nonlinear normal modes that are actually active in the response here. And again, why big N is not necessarily equal or does not have to be equal to little n. All right, so we are going to proceed by defining new complex variables for each component, which will be, we'll call this psi sub im, which is a function of t, and this will be equal to x dot im of t plus j times omega m times xim of t. Here, I need a little bit more space. M is equal to 1 all the way up to big N, and then I is equal to 1 up to little n. So if you go back and look at the notes on complexification averaging, this is exactly what we did on the example we did, where we created a new complex variable by combining the velocity of the oscillator with the displacement of the oscillator. So we're effectively just extending that idea here to the components or the modes of vibration at each degree of freedom. So from there, we can then take this new complex variable and partition it into a slowly varying complex amplitude, which we'll call phi sub im of t, and that modulates a fast oscillation. So we can write that as the psi im of t is equal to some phi im of t times e to the j omega m t, where here the phi component is slow, we'll just say slow component, and e to the j omega is our fast component. And you should see similarities to what we did in multiple scales, and if not, you should go back and check that, where we were always decomposing into some slowly varying amplitude times some fast oscillation. We're doing exactly the same thing here, except now we're doing it to components of a response, or each mode of a response, rather than the response itself. Okay, so everything we've talked about so far is all analytical, meaning you do it with the equations of motion, assuming you know what they are, or assuming you have some analytical decomposition of a dynamical system. We're now going to do this empirically, where we'll employ the Hilbert transform and wavelet-bounded EMD as well. Okay, and then we're going to end up showing how we can construct the slow flow dynamics using IMFs directly and show how they correspond to the analytical slow flow dynamics. Okay, so first let's just remember from chapter 8 that the Hilbert transform can be used to construct analytic signals, which you can then decompose into a polar form. We're going to apply that same idea to the IMFs extracted using the wavelet-bounded EMD. So we're going to start by assuming that each degree of freedom has been decomposed into sets of IMFs. For this discussion, we're just going to assume that every degree of freedom has been decomposed into the same number of IMFs, but that doesn't necessarily need to be true, or you could have an IMF that is just 0 because a particular mode isn't active at a particular degree of freedom. In our discussion, we're just going to assume that they all have the same amount, just to simplify it. Okay, so having done that, we can then reconstruct the original degree of freedom response as approximately using those IMFs, where xi of t is approximately equal to ci1 of t. That would be the first IMF of the ith degree of freedom, plus ci2 of t. This is now the second IMF of that ith degree of freedom, plus all the way up to ci big N of t, where here I is equal to 1, all the way up to n. So C sub im t is going to be our mth IMF associated with the frequency, fast frequency omega m for the ith degree of freedom. All right, so motivated by the discussion in chapter 8 and what we just talked about for creating these complex variables, we are going to complexify the mth IMF for the ith degree of freedom as follows. We will say that psi hat sub im of t is equal to C sub im of t. So the hat here just means that it's empirical, not analytical anymore. Ci sub im of t plus j times the Hilbert transform of C sub im of t, which we'll define as being equal to some complex amplitude A sub im of t times a fast oscillation e to the j theta sub im hat, also a function of t. And by construction, by using that Hilbert transform, this is an analytic signal, which therefore allows us to do that polar decomposition. So you'll notice that this is a slightly different complexification than what we did for the analytical slow flows, and we're going to get back to that point in a moment. So now that we have this complex variable, we can calculate the instantaneous amplitude and phase as the following. So we're going to, for the amplitude, we have the square root of Cim squared of t plus the Hilbert transform of Cim of t, that quantity squared, and we take the square root of that whole thing. And then the phase is computed as the inverse tangent of the Hilbert transform of Cim of t, and we're using these little curly brackets, divided by Cim of t. Okay, and then instantaneous frequency we'll just compute as the derivative of theta hat with respect to time. Okay. So we're going to partition this complexified IMF into slow and fast parts as follows. So we'll have psi hat sub im of t being defined as here a hat sub im of t times e to the j times the quantity theta hat sub im of t minus the fast frequency omega m times t. All of that multiplied by e to the j omega m t. And then everything to the left here is our slow component. And then everything in the right here, this is the fast component. Okay, we're now going to look at a different complexification, the one based or similar to what we did in the analytical system when we constructed analytical slow flow dynamics. And in this case, we're going to say here that Cim dot of t, so that is the time derivative of the mth IMF at the ith degree of freedom, plus j omega m times Cim t, which in this case we can decompose this as a tilde sub im of t times e to the j theta tilde im of t. And so this format, or this complexification, is similar to what we did for the analytical slow flow. Okay, so if this complex function psi tilde is analytic, then so will be the function j times psi tilde im of t, which is then equal to minus omega m of cim t plus j times c sub im dot of t. This then implies the following, that c sub im dot of t must be equal to minus omega m times the Hilbert transform of c sub im of t. And so Micah, you asked why don't we just do filtering last week? And the reason is that this kind of relationship, because the IMFs are special based on the way they've been defined and extracted, we're able to relate the velocity directly to the Hilbert transform of the IMF itself, which we'll then be able to use to establish this equivalence between the analytical slow flow and the empirical slow flow that we're working on now. Okay. So if equation 24 is satisfied, then there is an equivalence between the analytical decomposition that we saw previously and the empirical decomposition that we just did, and it follows that the component xi m of t is equivalent to the IMF c sub im of t, and the component velocity x sub im dot of t is equivalent to the IMF velocity. So from there we can rewrite equation 22 as c sub im dot of t plus j omega m c sub im of t, so that's just rewriting what we had before, is now equal to minus omega m times the Hilbert transform of c sub im of t plus j omega m c sub im of t which we can then rewrite as j times omega m times the quantity c sub im of t plus j times the Hilbert transform of c sub im of t is then equal to j omega m times psi hat im of t. And so what we find is that psi tilde sub im of t is equal to j times omega m times psi hat sub im of t. And from that, we find that the analytical slow flow dynamics, which is what we would really want to study if we could, can be expressed as phi sub im of t is approximately j times omega m times a hat sub im t times e to the j times theta sub im hat of t minus omega m of t. So what this establishes is that using wavelet bounded EMD or just EMD in general and getting IMFs, we can then extract the slow flow dynamics directly from some simulated or measured response, which we can then use to study nonlinear resonances. And also you can do reduced order modeling and other things with this as well. The key thing here is that you can use the IMFs to construct that underlying slow flow dynamics, which has kind of been a core thing that we've dealt with throughout this class in general. Okay, any questions? All right, that's a lot to take in. Like I said, Thursday you'll do a worksheet where you'll apply this. And then there'll be a homework on this kind of stuff as well. All right, so we're now going to combine the results from the averaging theorem with the correspondence or equivalence between the analytical and empirical slow flow dynamics. And this will then allow us to uncover these nonlinear resonances that's been captured in some type of measured data or simulated data. All the examples I have are simulations, but you'll deal with experimental data on Thursday and in the homework as well. Okay. So if you recall, for a system with two angles, two fast frequencies, and each with their own slow frequencies, the resonance condition is given as k times omega 1 minus L times, so this should be plus L times omega 2 equal to 0, true for k, L in being integers. And this will only hold if one of those two integers is negative. And as a result of that, we can reduce the possible types of resonances that can occur. Okay, so first I listed two cases here, and those two cases are equivalent actually. So that already reduces it down by 1. And as a result, we can rewrite our resonance condition as k times omega 1 minus L times omega 2 is equal to 0, and now k and L now live in the space of positive integers, which then leads to a special phase variable, which we'll write here as phi k to L is equal to k times theta 1 minus L times theta 2. Okay, so that was established for a case where we only had two fast frequencies and therefore only can create a single special phase variable. We're now going to expand that to account for degrees of freedom and multiple components at each degree of freedom. Okay, so doing so, we're going to define a special phase variable using the empirical slow flow dynamics, and that special phase variable will be phi hat. And then in the subscript, we have r dash p comma s dash q, and in the exponent, we have k to L. Okay, so we'll write out what this is, and then I'll talk a little bit about what it is. So this is then equal to k times theta hat of r dash p of t minus L theta hat of s dash q of t, and here k comma L live in the domain of positive integers. Okay, so theta hat sub r dash p is the pth IM, or the phase of the pth IMF for the rth degree of freedom, and then similar for s and q. All right, so I mean, it's kind of a dense nomenclature, but it will help if you're dealing with many degrees of freedom and trying to map interactions from one degree of freedom at one mode to another mode at another degree of freedom, which we will do in a moment. All right. So we can define this phase variable for any combination of R and S and P and Q. However, the number of combinations that should be investigated should be reduced and can be reduced just by knowing what kind of basic frequency content is captured by the signal. Meaning you should do a wavelet analysis and maybe a maximum wavelet transform analysis as well to determine what is contained in each signal that you're trying to analyze, so that you can narrow down the combinations of resonances that you're interested in. Also having, if there's an underlying linear system, having knowledge of that system's linear normal modes or its linear natural frequencies can go a long way as well for determining the types of resonances that can arise. And so doing some analysis before you start to play with these phase variables will save you a lot of time. Okay, so in the context of nonlinear vibrations, we're going to consider kind of three different cases. The first is where P here is not equal to Q and R is equal to S. So what this means is that we have different IMFs, potentially different nonlinear normal modes, and we're looking at the same degree of freedom. So in this case, what we're really trying to study is there an internal resonance between the pth and the qth NNMs, or if they're not NNMs, then just whatever components they are, whether they're higher harmonics or something else. This is what we're trying to study, is this internal resonance. If the case where P is equal to Q and R is not equal to S, and in this case we'll have the same IMF we'll say same component and different degrees of freedom. And this is a case where you have what's known as a resonance capture, which may either be a transient resonant capture, meaning that it dies out over time, or a sustained resonant capture, meaning that it lasts for the entire duration of the signal, if not longer. But you have a resonance capture between the Rth and S degree of freedom that is facilitated through the Pth NNM. So what this means is that energy gets transferred from one of those degree of freedoms to another, and it could be exchanged back and forth. It might be irreversible, and that exchange of energy is facilitated through that Pth NNM, or the Pth component, which is equal to the Qth component. And then there is a third case here where we'll have P not equal to Q and R not equal to S, and this is where you have different components interacting and also different degrees of freedom. So then this is a resonance where energy has been transferred between the Pth NNM at the Rth degree of freedom and the Qth NNM at the Sth degree of freedom. And the first example we'll go through is actually this case that we'll see. Okay, so once we have computed this special phase variable, we will plot it against time and look for what is known as non-time-like behavior, or a slow phase. We then also compute a phase velocity and plot the phase trajectory. And we look for little loops in it, actually. And that indicates the existence of a slow phase, which then tells us the averaging theorem fails, and then that tells us that there is a nonlinear resonance that exists in the response. All right, so just to sketch out what this will look like, we might have something that looks like this, and in this case, this portion as well as this portion, these are what we will say is time-like, meaning they grow just like time grows, and also they may be negative at a particular time as well. They may decrease negatively. What matters is the slope, that the slope is large. It's proportional to time, effectively. And then this middle region, we will say that this is our non-time-like behavior. Because it stops evolving like time. And generally what you'll find is that there's little oscillations in it as well. When we go and plot the phase trajectory, what we'll find is something that looks like this, where these arrows indicate the direction of increasing time, and these loops here, those indicate the existence of a resonance. And what kind of resonance is established based on how you defined this phase variable?
So when you refer to the time, like you refer to these branches that's going up?
Yeah, so, if you were to plot time versus time, you would get, 45-degree line.
This is because it's horizontal, it's not like.
Right. So if we go back just a little bit, where I have a fast frequency. So if you were to plot, all right, we'll just go with red. If you were to plot this fast frequency here, you're going to get something that's proportional to time, is the basic idea. And then this quantity, this total quantity, if it's slow, should not be, if there's no slow phase in it, then it's just going to be 0. If there's only a fast frequency. Otherwise, it's going to be non-time-like. And you will see this in the examples that we show as well, these plots. Any other questions? Okay. All right, so in the case of forced vibrations, you can also define special phase variables between the forcing and components in the response as well. If the forcing is monochromatic, meaning it's only a single frequency, then you can just directly apply the Hilbert transform to that, find the instantaneous phase, and in that case you can define a phase variable. Let me put a little hat here, phi hat sub r dash p comma f. That f is just forcing generically here with the ratio k to l, and so this is equal to k times theta hat r dash p of t minus L times phi sub f t, we need a hat, we'll add an f there. Again here K and L live in the space of positive integers. And so again, this phi sub f is just a phase of your forcing. The f doesn't mean anything special other than forcing. And we do the same thing then. We inspect the phase plot and the phase trajectory, look for non-time-like behavior or little loops, and that allows us to establish these resonances. And if your forcing is multi-harmonic, then you should decompose it using EMD or wave-bounded EMD, just like you would for the response data. And if there are multiple external forces, then you just extend the method as you would expect to extend it, similar to what we've done with multiple degrees of freedom. Okay. That being said, I'm going to go through just a summary of the general procedure, and we are starting with response data that has been either from some simulation or some measurement that you've performed, and what we want to do is characterize the nonlinear resonances that are contained in that response data. So from there, what we're going to do is we're going to take the response data and we're going to apply the wavelet-bounded EMD. If you really wanted to, you could just do regular EMD, but with a masking signal, and you're better off just using the wavelet-bounded EMD and saving time, but not to say that you couldn't do it. We're going to extract here monochromatic, meaning singular frequency, monochromatic IMFs. From there, we are going to take the Hilbert transform, and extract out the instantaneous amplitude, phase, and frequency. You might as well do all three. You lose nothing by doing it. And you can use the amplitudes to look for this beating type phenomena that we've seen before. From there, we're going to do a slow flow analysis. Meaning we're going to ask, are there any slow angles in the response? Again, looking for this non-time-like phase and loops in the phase trajectory. So in this context, you will be defining your phase variables yourself. You will need to know something about each of these components, what their fast frequencies are, what the ratio is between those fast frequencies. You generate this using basic knowledge of the underlying linear structure, and then doing like a wavelet analysis on the system. You can also take the instantaneous frequencies that you extracted from the Hilbert transform and try dividing them by each other to look at different ratios, provided that you account for errors that occur due to mirroring or end effects or a component dying out in the response. Okay, so from here, we're going to split this into two branches. This top branch, we're going to say, yes, there are slow angles. At that point, we can conclude that the averaging theorem fails. That tells us then that there is a resonance in the response for the particular ratio and degrees of freedom and IMFs that we've chosen. That resonance does exist. Which then allows us to characterize at least one of the resonances that exists. For the opposite case, which is for there being no slow angles, the averaging theorem holds. With the averaging theorem holding, that means that there is no resonance in the response. Which then allows you to eliminate a particular resonance as being a possible, just being existing in that response at least. Doesn't necessarily mean that it couldn't exist in another response, but in that particular one it does not. And then you can use this to try and understand what physically is going on in the response of a structure. All right, any questions before we go through some examples?
So we whack it, and then we're just looking at a blob of data, we don't know anything. So then we go through this whole rigmarole excite at some frequency?
I mean, that depends on the context of what you're trying to do. You know, if you are trying to uncover why a part is cracking or something, that could tell you that there's some resonance from the low frequency to a high frequency that's causing a stress concentration at a particular point. And so now you need to modify the design somehow to prevent that. Or you could do the opposite of trying to leverage those energy exchanges to harvest energy or dissipate or mitigate unwanted vibration. It really depends on the context. All right, any other questions? Okay. So in that case, we're going to consider the following example, which here is consisting of two masses. First mass is grounded with a linear spring and linear damper. We're just going to call this the linear oscillator or the LO, just kind of following similar terminology that we used previously. Connected to it is what we'll call the nonlinear oscillator or the NO. In this case, we have a linear stiffness of 0.1 coupling them and a nonlinear stiffness of 1 coupling them, and they both have weak damping. I gave you guys the equations of motion as shown there, and we're just going to simulate this response for 0 initial conditions, except that x dot, which is the velocity of the first mass, is equal to 0.5 in this case. And we are simulating from 0 to a time of 1,000. This is all non-dimensional, so there's no seconds in here. And we're just using a sampling rate of 10. So we're going to compute, first we're going to start by computing the underlying linear natural frequencies. We'll use that as a way to determine possible resonances. From there, we will plot the displacements, the wavelet transform, and the maximum wavelet transform for each mass. And we'll use that to determine characteristic frequencies that we need to do this wavelet-bounded EMD decomposition. We'll then do that decomposition, and finally we'll study two special phase variables, and we'll end up showing that there's a 3-to-1 internal resonance in this case. Okay, so first on the next page you can see that we're just constructing, first we're defining all our parameters, and then we're constructing a linear stiffness and linear mass matrix, and then computing the natural frequencies. In this case, we're leaving them in radians or radians per non-dimensional time, and then just computing their ratio. And in this case, the ratio is 3.5, a little bit above 3.5. And so we can say here that the ratio is approximately 3.5, such that the system could encounter a 7-to-2 internal resonance between those two modes. A 7-to-2, a 3-to-1, a 5-to-2, a 2-to-1, or a 1-to-1 internal resonance between the two modes, the two NNMs. So we can do this here because that linear coupling series is non-zero. If that coupling stiffness is 0, which it will be in the next example, you can't do this analysis because one of the natural frequencies is 0. And as a result, the ratio is infinite. Okay, so what tends to happen, this is a hardening nonlinearity, so the nonlinear frequencies are going to increase as energy in the system is increasing. And so if we start off with a 7-to-2, because that's equivalent to 3.5, what we expect is that one of these NNMs will increase with increasing energy, such that this ratio will go down as energy increases. And that's where the 3-to-1 can pop up. And then the 5-to-2, 2-to-1, and 1-to-1 are we're just kind of guessing that those could possibly occur. That's the point, 3.5 and 3 to 1, we can say will probably occur because of that ratio there. Below that, it's going to depend on how the other modes are changing. So again, you really need to study what's going on in the response. Okay, so here is the displacement response, the wavelet transforms, and the very bottom is the maximum wavelet transform of this. You can see that, although you can see there are 2 components in each of them, and if we just look at the displacements, there's also a beating going on. Specifically, let's draw it right here. There's this beating behavior like that for the NO, and the LO is something like that. Okay, so again, this kind of beating response is an indication that there's some type of resonance going on between these 2 components. Looking at, if we just look here at the maximum wavelet transform, you'll see we have kind of a maximum component there and a maximum one here, and they're kind of roughly a 3 to 1 ratio. And if you recall from multiple scales, we said that resonance doesn't require that they be exactly a 3 to 1 ratio, and they just need to be close to this ratio. All right, so in this case, we can say that the characteristic frequencies are 0.065 and 0.165, and these are the frequencies that we're going to decompose at. Those are the inputs to the wavelet bounded EMD. Okay, so on the next page I have here on top I have the 2 IMFs for the LO. You can see how they represent a particular component. And on the wavelet transform of the IMF, I've included the instantaneous frequency as that red line. All right. Oh, and one thing I will say is that in the top right plot, it looks like the IMF is a much faster frequency than what the original LO response had. At least that's what it looks like on the iPad. That is actually just an optical illusion. It's not actually the case. And we can try and zoom in here, which you may be able to see, but it actually lines up and overlaps quite well with that. So if it looks like it's way faster, that's just an optical illusion. It's not actually true. All right, so beneath that are the comparison between the IMFs of the 2 components for the NO. And you can clearly see here that beating behavior in that first IMF, whereas there's actually no beating behavior in the second IMF, as shown here. Okay, I'm going to show the second let's look at the second IMF of the LO. You can see here there is this beating response, which lines up with the beating response here. And so given this, what we're now going to look at is interactions between the second IMF of the LO and the first IMF of the NO. And by the way, I have switched the order of the IMFs such that the lowest IMF corresponds to the lowest frequency, and the highest IMF, or the second in this case, corresponds to the second highest frequency. And again, that just makes it easier to compare these with standard vibration terminology and what we think of when we think of nonlinear and linear normal modes. All right, so we're going to try and look for interactions between those components because they exhibit this beating phenomena. Okay, So like I said, there appears to be some type of internal resonance between IMF1 of the NO and IMF2 of the LO. And so we're going to define our special phase variable to be phi hat k to L with a subscript of 2-1, so 2 being the second degree of freedom, or the NO, 1 being its first IMF, and first degree of freedom, second IMF. And this will be equal to K times the phase of the first IMF of the second degree of freedom times T minus L times theta hat 1-2 of T. Okay. Also, the signs of K and L that we'll choose does not matter. We could flip the right-hand side of that equation and it would still be valid, and it would give us the same answer. We're going to consider two cases. The first will be the case of a 2-to-1 internal resonance. That's where K is 2 and L is 1. And the second case will be that 3-to-1 internal resonance that the problem statement claims exists. All right, so on the next page, I've already gone and computed this phase variable in the code. We're then plotting the 2-to-1 phase, and then on the right, we have the 2-to-1 phase trajectory. And here what we find is that this is just time-like. There's no real slow variation here. This is all very time-like. And there are no loops that occur in the phase trajectory. So one thing I will add is that if you recall with the Hilbert transform, we are filtering the instantaneous phase typically. And so if you don't filter enough, what you will find is that all of these little peaks here, these will actually be loops. And so what matters though is that the loops need to persist through that filtering. And you'll see what cutoff frequency I used here. And what we'll see in the next plot, what this non-time-like behavior looks like. So my point is that just because you find loops to begin with for a particular cutoff frequency in your filter doesn't mean that those loops actually do exist. You should go and analyze and do additional filtering. And generally what I like to do is I like to make sure that I check against the wavelet transform that the instantaneous frequency makes sense. If I hadn't filtered this enough, my frequency would do something like that. And then I know I haven't filtered enough. And the same thing with the amplitude. If I hadn't filtered enough, then I know the amplitude would not match as well. So you can tune your filtering to match what's in the wavelet transform as well as what's in the time domain. Generally, that's what I like to do. And once I have something that I can accept and I trust, then I start to construct these phase variables and analyze the phase trajectories. Okay, so we'll say here that since the phase, we're going to just finish this problem and then we'll do the others on Thursday. We're almost done. Since the phase only shows time-like behavior, there is no 2-to-1 internal resonance in the response. Okay, so what we're now looking at is these phase variable for a 3-to-1 internal resonance. And here in the beginning, we have a time-like behavior, as well as at the end here. But in the middle, we have some non-time-like. And if we go look at the phase trajectory, we'll find that there are a collection of loops in there, which again indicates that there's a slow frequency or slow phase variable leading to the failure of the averaging theorem, which tells us that indeed there is a 3-to-1 internal resonance here. And by the way, this point is called capture. And then here we are escaping that resonance. And this point right here lines up somewhere around here. This one lines up like over here. In the code, you can find exactly when they are. I didn't write that down. And we'll say that again, this is non-time-like. And the last thing we'll say that is that the appearance of loops indicates that there is a 3-to-1 internal resonance in the response. And because of how we defined it, we now know that the second NNM in the LO is exchanging energy with the first NNM in the NO, in the nonlinear oscillator, based on the way we defined our phase variable. What you could then do is study, does the second NNM pump energy or exchange energy, second NNM of the LO exchange energy with the second NNM of the NO. You can do things like that as well.